Hello, I'm Isabela Fernandez and welcome to my Physics 2211 Lab 1 of Constant Velocity. Introduction. So first, to establish the purpose of this lab, we were supposed to observe the motion of some object that is moving at the same speed without changing its direction and capture a video of its motion. There are several fundamental principles involved. To start off, Newton's first law of motion states that an object at rest stays at rest and an object in motion stays in motion with the same speed and direction unless acted upon by an imbalanced force. Also, Newton's second law of motion describes the motion of an object produced by unbalanced forces. The net force acting on an object is equal to the product of its mass and acceleration. Both of these laws are used to explain physics concepts seen in this lab. Using Newton's second law of motion, we can arrive to several conclusions. So if F net equals mass times acceleration, we know that acceleration equals the change in velocity over the change in time. So we can write that equation as F net equals mass times the change in velocity over the change in time. We also know that the change in velocity equals velocity final minus velocity initial, so we can denote that as well. We can rearrange this formula and come up with an equation for the final velocity of an object, which equals its initial velocity plus F net over its mass times the change in time. Also, if we distribute the mass in velocity final minus velocity initial, we know that mass times velocity equals the momentum. So we now have a formula for the change in momentum as well. Tracking the observed motion. Using the app of Tracker, we're able to calculate the motion of the object with the axis labeled in purple and the red dots that label the position of the marker and its trajectory. And we can see here that this position time graph is not completely linear, tracking the predicted motion. Using GlowScript, we were able to come up with a computational model that predicts the motion of the marker. As we can see in this video, the object moves in a horizontal direction. And in the right, we can see that the position versus time graph is completely linear and the velocity versus time graph is constant. Using GlowScript and the time frames and the position of each time frame, we were able to denote another graph that shows the predicted motion. And we can see here that it is completely linear, unlike the other graph of the observed motion. So in order to build the computational model, we needed to code using Python. This part of the code is to visualize and initialize the graph. In here, we denoted the mass of the marker in kilograms. We also stated the initial position vector calculated with the app of Tracker and the initial velocity, which was calculated with the initial position and another position in a time frame and over the change in time. Here we created a while loop to predict the motion. We also labeled our net force to be 0 given that the object is moving at a constant velocity. Using the updated formula for velocity I showed when explaining Newton's second law, we were able to come up with this final velocity formula too. I also changed position to be in terms of velocity as well. Analyzing and comparing motion. Here is a graph that compares the observed motion, which we can see in blue, and the predicted motion, which we can see in orange. And we can clearly denote that the observed motion has a steeper slope than the predicted motion. And this is because there are some errors that need to be accounted for that were not accounted for in this lab experiment. For example, there may be some human errors that I may have done when doing this lab, but most importantly, the physics behind these errors is that the slope of the predicted motion is much steeper than the observed motion because in the computational model, which is the predicted motion that we see in orange, we did not account for other external forces that may have acted on that object. For example, we did not account for friction or air resistance, which are also acting on that system because we assumed that the net force of that object was 0. Conclusion. So now we're going to discuss what if we switch the direction of the x-axis. If we would switch the direction, the position would travel the same distance, but it would have the same magnitude, but it would be in the opposite direction, and that would be the same for the velocity vector as well. And what does all of this lab experiment mean? Well, we can conclude that if an object is traveling at constant velocity, that means there is no change in velocity, and that means that there is no change in momentum. So eventually, there will be no net force acting upon the object, and the force will be zero. However, that shows that our computational model was not 100% accurate because we can't determine all the forces that act upon the object because we cannot account for them given that they can escape during observation. Hope you enjoyed and thank you for listening.